Welcome to this session 2. See, in the session 1, where I've written this as 1, actually I've discussed about the DWSIM platform in which we had seen two unit modules, shortcut distillation column and short dist decol, which is rigorous distillation column. Where do we find them? That is the reason I've mentioned that as a session 1. Now this is session 2. In the session 2, what are you trying to, or what are you able to see? See here, let me, okay, let us come up with our problem session here. So this is the problem now we are looking at. Okay. A problem itself, or in the distillation column, what we want to solve. And where did I take this as a what you call resource? I have taken it from a book called what do you say, Separation Process Principles, written by Cedar, right? So here, what does it say? If you can look at this, this is the feed, this is the feed, and it is entering at bubble point. So it is a mixture bubble point, and the pressure is given as pressure is equal to 55 psia, and the molar flow rate, the feed molar flow rate, that is F is equal to 620 pound moles per hour. This is the one, and ultimately the composition, that is ZF, or generally we refer ZF to be as the mole fraction, the more volatile component in the system. Here the system what we have taken is benzene, okay, benzene plus toluene. But you should be very careful. This benzene is the more volatile component, as its boiling point is around 78 degrees centigrade approximately, and this is 108 degrees centigrade. So definitely the boiling point of benzene is less. We say it is more volatile compound. So ZF, it represents the 0.46, or it is given as 46 mole percent. It represents the 0.46. So what is our intention in this particular problem? See, intention or design intent, or whatever it is, we can call. Now, given the feed conditions, feed ZF, it's what you call entering at which conditions, that is temperature and pressure, and of course feed is F means flow rate, and what is the what you call reflux ratio. We need to specify the at least a reflux ratio. We need to know at least small amount of this one, and this is reflux ratio we have to know. And for such binary systems, we need to understand it is to be taken from the design conditions. Generally, it varies from, I think you all know, 1.5 to 2.5. And of course, the distillate, in the distillate, how much is the composition of the more volatile component, and in the bottoms, that is, this is the bottoms, you can see, and this is the distillate, this is the distillate, and this is the bottoms, and how much is the mole fraction or the real composition of the more volatile component. See, I am referring to it as more volatile component only, but in simulations you should be aware of something called, they mention it as light key and heavy key. So definitely light key would be the more volatile component, heavy key would be the less volatile component. Why they are calling it as a key component? Because in the top, in the top product, we want HK, that is heavy key component, less than or equal to, suppose, say 0.02 mole percent. That means definitely the light key component should be 98%. And in the bottom product, light key generally in the specifications of the simulation columns, you should be understanding this terminology. Light key, you need to mention whether it is less than 1% or less than 2%, less than 5%, depending upon the requirement. So this is the problem description as of now. Okay. So let's go ahead and let me read the problem here for the sake of understanding better. A representative binary distillation is shown in the figure. That means you have seen for the separation of 620 pound moles per hour of a mixture 46 mole percent benzene and from 54 mole percent toluene. The purpose of the 80% efficient 25 C3 column and the partial reboiler that acts as an additional theoretical stage, this is very important, is to separate the feed. Now what do we require? Separate the feed into 99 mole percent benzene and the liquid. This is distillate, and the liquid bottoms of 98 mole percent toluene. In the bottom is at 98%. The column operates at a reflex drum pressure. It is giving us a reflex drum. That is top pressure. The reflex ratio. No, this is RR. We need to at least specify this reflex ratio. And this is one. And then if an infinite number of stages were used, the required reflex ratio, that means this would be the R minimum. So we can know R by R minimum for such systems, it is actually mentioned here as 1.297. And of course, the feed condition is given. The feed condition is bubble point and at pressure 355 psi, and it is in SI units also, and 294 Fahrenheit. See, bubble point, that means what could be the bubble point here? 294. A total condenser. Now here, see, look at this. A total condenser is used to obtain saturated liquid. That means total condenser here, this has a specific theoretical implication. And a liquid distillate at a bubble point temperature like this. The heat duty of the condenser. See, generally our intention in such, such distillation, such simulations would be majorly to find what is the heat load in the condenser, what is the heat load in the reboiler. And of course, given feed, we need to find what is distillate and what is residue. Okay. And then check with the specifications whether it is met or not. Whether it is met or not. For a given reflex ratio. The reflex ratio is given, feed flow rate is given, and ZF, feed mole fraction is given, feed temperature and pressure are given, condition is given, and these things are the conditions which are given, and we will estimate or we will try to find it. And these are to be specified. These are these design specifications. These are the given inputs. Okay. Specifications are also part of the inputs. Okay. We will actually solve the problem in the next session. Okay. Bye.